Today we're going to learn about weak acids and bases. This is an important application of the equilibrium chemistry that you've been learning about. So some of this stuff's going to seem familiar to you. It's actually not too hard if you're pretty comfortable with equilibrium chemistry. It's just a new application of something we've been doing before. And it's actually a very important one. So let's talk about weak acids and contrast them with strong acids to get started. Weak acids, they behave just like strong acids do, except they reach dynamic equilibrium with hydrogen ions and the conjugate bases that are left over after they ionize, or with hydronium ions, depending on how you're looking at it, how you're modeling it. So a strong acid, for example, if it's some generic acid, HA, it's going to fully dissociate and it's going to produce H plus ions and A minus ions. A weak acid, on the other hand, let's call it HB, is going to produce the same ions, hydronium or H plus ions and B minus ions, the conjugate base, except for it's going to do it reversibly. It's going to reach a dynamic equilibrium. So for example, hydriodic acid, HI, is going to completely ionize into H plus ions and I minus ions. Whereas hydrofluoric acid, which is a weak acid, will break up into H plus ions and F minus ions when it ionizes, but it'll do that and reach a state of dynamic equilibrium, and actually fairly soon, and that's why it's called a weak acid. Here's the alternative notations for that. This is actually more technically correct. The HI and the HF are both reacting with water to produce hydronium ions. They're not just splitting up into hydrogen ions and the conjugate base. But you can model it either way, and I'm most often going to choose the old-fashioned way with just modeling it as H pluses, not H3O pluses, because I think it's a little bit easier to visualize. Because this is at dynamic equilibrium, there's an equilibrium constant, just like there always is. So, for example, if you have a generic weak acid HA and it's ionizing to give you H plus ions and its conjugate base, which would be an A minus ion, the K for this equilibrium would be H plus and A minus concentrations on the numerator and HA concentration in the denominator. You'll notice that it doesn't say Kc, it says Ka. That's a special notation that we give to acid equilibria. If you're using the modern notation, where the HA is reacting with water to produce hydronium ions, the form of Ka still is the same form. You have hydronium instead of the H plus, but everything else is the same. And the reason is because water is a liquid and it does not appear in the expression for the equilibrium constant. The name for this equilibrium constant is called the acid ionization constant, or sometimes people call it the acid dissociation constant. I will often use that terminology rather than acid ionization constant. They mean the same thing, and Ka is the simpler way to just refer to it every time. You can compare the strengths of weak acids relative to each other by just comparing their Kas, because the larger Ka means more products, and among those products are hydrogen ions, and the more hydrogen ions you have, the stronger the acid. So between these two, for example, nitrous acid, HNO2, and hydrogen cyanide, which is also an acid, the Ka for HNO2 is 4 times 10 to the minus 4th, whereas the Ka for HCN is 10 to the minus 10th. Obviously, 10 to the minus 4 is much, much larger than 10 to the minus 10, and so HNO2 is going to be the stronger of these two acids. Let's work out some problems. This first question is asking us, what's the pH of a 0.1 molar solution of HNO2? And the Ka, you might remember, is 4 times 10 to the minus 4. So we're going to set this up with an ice chart. So I'm going to write down my equation for this dissociation. This is going to be HNO2 aqueous, and it's reversibly dissociating to give you H plus ions, aqueous solution, and nitrite ions, and NO2 minus, aqueous as well. Initially, well, this is a 0.1 molar solution, so my concentration of HNO2 is 0.1. I don't have any of this until ionization takes place. Then my change It's one-to-one stoichiometry, so I lose X moles of HNO2. I'm going to gain X moles of hydrogen ions and of nitrate ions. So at equilibrium, I'm going to end up with 0.10 minus X, and X for both the H plus and the NO2 minus. So Ka, the expression for Ka, remember, is going to be concentration of H plus ions times concentration of the nitrite ions in the numerator, and then in the denominator, I have the concentration of HNO2 at equilibrium. So plugging in numbers here, 4.0 times 10 to the negative 4, that's our Ka. In the numerator, I have X times X, so just X squared. And in the denominator, I have 0.10 minus X. It's probably pretty reasonable to make the assumption that X is going to be very small compared with 0.1, so I can drop it, which means that if that's a legit approximation, 4 times 10 to the minus 4th is approximately equal to X squared over 0.10. So now I'm just solving for X. So I will take 0.1 times 4 times 10 to the minus 4, and that just gives me 4 times 10 to the minus 5. And that would be approximately equal to X squared. So then we find out what's the concentration of H plus by solving for X, because that's one of the things that X means here in this equation. So we're going to take the square root, and we end up with X equals 0.0063. 0.0063 is in fact very small compared with 0.1. It's much less than 5%. So my assumption was valid, and we can go with this. All right, so if the concentration of H plus, we have just now established, is equal to 0.0063, because that's what X means here, then that means pH, which is the negative base 10 logarithm of concentration of H plus, is the negative base 10 log of 0.0063. And that number is 2.20. Remember, I'm taking the log of a number that has two significant figures, so that means the number that I end up with is going to have two decimal places. That's the sig fig rule there. This problem is almost the reverse of the last problem. Here we want to know what Ka is. We don't know it, but we do know what the pH is. We're going to start out by making a Rice chart. It's a pretty good general way to do that. We don't know what the acid really is, so we'll just model it with a generic HA. So HA, aqueous, is going to, because it's a weak acid, reversibly reach dynamic equilibrium with H plus A minus. And again, we don't know what A is here because this is just some generic weak acid. We aren't told its name. Initially, the concentration of HA is 0.200. Before it ionizes, there won't be any of the two products. Change is 1-to-1, so minus X plus X plus X. And at equilibrium, this will be 0.200 minus X, and this will be X, and this will be X. So Ka is going to be concentration of H plus times concentration of A minus, whatever those are, divided by the concentration of HA once we reach equilibrium. But the concentration of H plus and the concentration of A minus are just going to be X, and the concentration of HA is 0.2 minus X. Ka, we just don't know what it is. However, we do know that the pH is related to the concentration of H plus. So concentration of H plus, that's going to be 10 to the minus 4.07 because of the definition of what pH is. If pH is a minus base 10 logarithm of H plus concentration, then H plus concentration is 10 to the minus pH. So that number is 8.5 times 10 to the minus 5 molar. That's the concentration of H plus. And in this chart, X corresponds to concentration of H plus. So in our chart here, Ka is going to be X times X. So that's going to be 8.5 times 10 to the negative 5 times itself, and then divided by the concentration of HA, which is 0.200 minus 8.5 times 10 to the minus 5. But that's so small compared with 0.2 that we can either subtract it or just forget it, because it's not going to change the value when we're using significant figures properly. So now we can just solve this problem. You can put the minus 8.5 times 10 to the minus 5 in the denominator if you want to, but it's certainly not necessary. So we square the numerator, divide by 0.2, and come up with our answer. So Ka here is 3.6 times 10 to the minus 8. Here's another type of problem that you're sometimes asked to do. Find the percent ionization of a weak acid. So we want to know what's the percent ionization of a 0.2 molar solution of this acid here. This is acetic acid, and the Ka is given to us. So to find a percent ionization, you just kind of use some common sense, and you know what percent means, and just think about what that might possibly be calculated by. But start with a Rice chart. So for this acid, which is HC2H3O2, it's going to reversibly ionize, going to give up a proton because that's what acids do, and then what will be left is C2H3O2 with a 1 minus, because it's 1 less H, 1 less charge. So there's the ionization equation. I've left off the AQ symbols. I'm going to start doing that more and more just to save a little bit of writing. But just recognize that these things are all in aqueous suspension. All right, initially, this is a 0.2 molar solution, 0.200. Neither of these are present. Our change, minus X plus X plus X. This should be starting to become pretty familiar to you. So at some point, you might start just dropping the ice chart, because you sort of know how these things are going to end up, especially with one-to-one stoichiometry. So at equilibrium, Ka will be equal to concentration of H plus times concentration of this ion. This is called the acetate ion, divided by the concentration of the acid, which was the HC2H3O2. So in terms of the numbers that we have here, Ka is 1.8 times 10 to the minus 5. In our chart, both H plus and acetate concentrations are X, so the numerator is X squared. And in the bottom, we have 0.200 minus X. And again, we're going to make this assumption that because 10 to the minus 5th is very small, the X in the denominator we can ignore to make a little simplification. You don't have to do it. You can solve the quadratic if you're comfortable doing that, and it makes you feel better, but it's completely unnecessary probably. And you can always check in the end to find out if it was an okay thing to do. So we'll solve this problem and find out what X is. I'm using the simplification, so I'm just going to 1.8 times 10 to the minus 5 times 0.2, and then I'm going to take the square root of that number to get X. And I come up with the value of X being 0.0020. So that's 2%, 0.2% of 0.2, or no, 0.1% of 0.2. So my assumption to drop the X in the denominator was fine. It was legit. All right, so now I know that X is equal to concentration of H plus, but I also know that X is the amount of concentration of acetic acid that ionized. So right there, it's the ionization, the ionized amount of this acid, this HC2H3O2. So I can take that value, the amount that ionized, and I can divide it by the amount that we started with, 0.200, and then change it to a percent by multiplying by 100, and I'll find out what percent was ionized. It's not going to be much. 0.002 divided by 0.2 is 0.01. So if I multiply by 100, I'll have 1. So this is a 1% ionized, 1.0 I should probably put. Not much ionized, and that's typical because it's a weak acid. This problem asks us to look at a mixture of two weak acids. There's HCN in there, the Ka is given, and HNO2, another weak acid, and the Ka is given for that. And the first thing it asks us is, what are the major species present in this mixture? So to find out which are the major species, let's first of all figure out what species are present at all, and then think about which ones will be the ones in the greatest concentration. So let's do the dissociation equations. HCN is going to dissociate or ionize to give you H plus Cn minus, and the HNO2, that's going to dissociate and give us H plus and NO2 minus. So what's present? Well, HCN molecules are going to be there. HNO2 are going to be there. There's going to be H pluses from both of the two acids. The HCN gives us the cyanide ion, Cn minus, and the nitrite ion, NO2 minus, also is going to be present from the nitric acid. And then water. There's going to be, water is going to be predominant because that's the background where all of this is taking place. All right, so now let's think about what things are present in the greatest concentration. For HCN, Ka is 10 to the minus 10th. That's really small. And so that means there's not going to be very much H plus or Cn minus present due to that ionization. And for HNO2, the Ka is bigger, but it's still pretty small. So the amount of NO2 minus and the H plus present from that ionization are also going to be pretty small. So there's going to be not much H plus. There's going to be not much of this, not much of this. Mostly at equilibrium, we have reactants. So there's going to be a lot of HCN. There's going to be a lot of HNO2, and then, of course, water. So these are the major species that are present in this mixture. The other things are present, H plus, Cn minus, NO2 minus, but just not very much of them, so they're not what we would consider major species. Now here's the next problem. It's asking, what's the pH of this mixture? Now, one thing you can do is you can consider the contributions of both the HCN and the HNO2, but if you think about this realistically, 10 to the minus 10th and 10 to the minus 4th tells us that most of the H plus, by far, the majority of the H plus is coming from the HNO2 ionizing. So I'm just going to ignore this and say, compared with the amount that we get from HNO2, this is going to be practically nothing contributed by the HCN because it's so much weaker of an acid. So I'm going to just set up a quick Rice chart. HNO2 ionizing to H plus NO2 minus. We know how this is going to work out. This concentration is 1. These are 0 before ionization. 1-to-1 stoichiometry. Equilibrium. 1 minus x, 1.00 minus x, and x and x. So at equilibrium, Ka, which is 6.2 times, wrong acid, 4.0 times 10 to the minus 4th is going to be equal to x squared over 1.00 minus x. And I'm going to make this simplifying assumption that says I can drop that x and ignore it to make my calculation simpler. So x is just going to be the square root of my Ka of 4 times 10 to the minus 4. And that's 0.02. And that is equal to concentration of H plus, because that's in our chart one of the things that X means here. So that means pH is the negative base 10 logarithm of 0.02. And that works out to 1.02 This was supposed to have two significant figures in it, so that's legitimate to keep those two. So that's the pH of this mixture. Now, if I wanted to just be really sure, I could then do a Rice chart for the HCN and find out how much H plus is going to be contributed. And if you do that, you will find out that it's so small compared with the 0.02 molar that it was perfectly fine to ignore it. So the next question that's being asked here is, what is the concentration of CN minus in this mixture? So the CN minus comes from the dissociation of HCN. HCN ionizes, it's going to make H plus CN minus. And we've already decided that most of the H plus that's produced here, by far the vast majority of it, does not come from HCN. It comes from HNO2. So how we're going to treat this is, in our initial line, we're going to use that concentration of H plus, which was 0.02. I erased it, but I recall that. 0.02 was the starting concentration of H plus, because that's the amount that was already there because the HNO2 dissociated, and none of this before ionization. The HCN concentration is 1 molar. The changes are going to be minus X, plus X, and plus X. At equilibrium, 1 minus X is concentration of HCN. 0.020 plus X is going to be the H plus concentration, and the CN minus concentration, which is what we want, that's going to be X. So Ka, which is 6.2 times 10 to the minus 10th for HCN, is equal to 0.020 plus X times X in the numerator, because that's H plus concentration times CN minus concentration. And in the denominator, it's 1 minus X. 10 to the minus 10th is enormously small. So that means this X here in the numerator, we can probably ignore it. In the X in the denominator, we can probably ignore that as well to simplify our calculations. So that if I do that simplification, then X is just going to be equal to 6.2 times 10 to the negative 10th divided by 0.020, because I'd be multiplying by 1 to solve that problem. So I'll take 6.2 times 10 to the minus 10, and I'm going to divide it by 0.02, and that gives me a value of X that's equal to 3.1 times 10 to the negative 8th molar, and that is the concentration of CN minus ion at equilibrium, which is what we were looking for. Weak bases are not a lot different than weak acids. They have a dynamic equilibrium with hydroxide ions, though, instead of hydronium or H plus ions. And then they have a conjugate acid rather than a conjugate base. If you remember, strong bases are all metal hydroxides that dissolve in water. They do it completely, and then you're going to get some metal ion, and then you're going to get hydroxide ions. What makes them bases is the fact that you get hydroxide ions. Weak bases are all going to be molecules that can only produce the OH minus by reacting with water. Sometimes they're not molecules, sometimes they're ions, but they have to rely on water to be an acid, a proton donor, in order to produce that conjugate acid. And then water is what actually provides the OH minus. So for example, here's a weak base, let's call it B, reacts with water. It reaches dynamic equilibrium with its conjugate acid, which we're just going to call HB plus. It's one more H and one more plus. And then the proton getting donated from HOH, that's water, leaves behind just OH minus. And so that's how the weak base produces hydroxide ion. Here's an example. NH3 is a weak base. It reacts with water. NH3 is called ammonia. It's a very common weak base. It produces ammonium, so it's NH4 plus, one more H, one more plus, and then the OH minus is left over from the water. So that's how weak bases work. Because this is an equilibrium, just like with a weak acid, there's an equilibrium constant. It's called Kb. and it's just the concentration of HB plus, that's the conjugate acid, times concentration of hydroxide divided by the original concentration of the base. And notice that water is not in the denominator, and again, that's because it's a liquid, so it does not appear in this equilibrium expression. The name for Kb is called the base ionization constant, or sometimes the base dissociation constant, but ionization is what almost everybody uses, or just refer to it as Kb. You can compare the relative strengths of weak bases, just like you can compare the relative strengths of weak acids by just comparing their K values. A bigger Kb means at equilibrium you're going to have more OH minus ions, and so that means it's a better base producer. It's a better OH minus producer, so a better, stronger base. So comparing these two, ammonia and CH3 and NH2, which is called methylamine, the CH3NH2 has a larger value of Kb, which means it's a stronger base than NH3, because 10 to the minus 4 is bigger than 10 to the minus 5. Let's work out some problems. The first one is going to be relating to pH and weak base Kb values. This is very similar to finding pH of weak acids, except just one more step really, because pH is based on hydrogen ion concentration, and Kb is in terms of hydroxide ion concentration. You just have to do a little converting at the end. I'm going to start out with a Rice chart. So I'm going to start out with the equation, the reaction that's happening here. C2H5 NH2 in aqueous solution. This is reacting with water and reaching dynamic equilibrium with the acid, conjugate acid, which is C2H5NH, not 2 but 3, and not neutral but plus OH minus. Initial concentration 0.10 molar. We don't care about water because it's a solid, it's not in our, or it's a liquid, it's not in our expression. This will be 0, this will be 0 before ionization. The change is 1 to 1, so minus x plus x plus x. At equilibrium, concentration of the ethylamine, that's the name of this base, is 0.10 minus x. Water we don't care about yet, and x and x. So Kb, the expression for Kb is going to be concentration of our C2H5NH3 plus, the conjugate acid, times concentration of hydroxide ion in the numerator, and in the denominator is going to be the concentration of our original base, C2H5NH2. So our Kb here is 5.6 times 10 to the negative 4. And in terms of the values in our chart, x squared is going to go in the numerator, and 0.10 minus x will go in the denominator. And again, you can solve the quadratic if you want. 10 to the minus 4 is pretty small, so I'm going to ignore that and simplify my calculations. So I'm going to take 5.6 times 10 to the minus 4 times 0.1, which ends up being 5.6 times 10 to the negative 5, and that's equal to x squared. So I'll take the square root of both sides and find out what x is. And x is, after that calculation, 0.0075. 0.0075 is, in fact, very small compared with 0.1, so my assumption was a legitimate assumption to make there. That is equal to concentration of OH minus. That's what one of the things that X means in our chart. All right, so if the concentration of OH minus is equal to 0.0075, then the concentration of H plus is equal to Kw, which is 1 times 10 to the minus 14, over that OH minus concentration. So that's equal to 1.3 times 10 to the negative 12. So that's H plus concentration. So that means the pH, which is what we are ultimately trying to find here, is the negative of the base 10 logarithm of that value, 1.3 times 10 to the minus 12, which we know is going to be roughly 12. It's 11.87. And I'm using 2 decimal places because I have 2 significant figures in the number that I took the log of. And just kind of a gut check on these kind of problems. We know this is a base, so that we know the pH should be higher than 7, and that checks out here. Here's our next problem. The pH of a 0.2 molar solution of a weak base is 10.92. What is Kb? So this is the opposite problem. We know the pH, but we want to know Kb. We'll start out with a Rice chart like we always do. B, let's call that our generic base. It's reacting with water, because that's what they do. Reaches dynamic equilibrium with its conjugate acid, which we'll call Hb plus, and hydroxide ion. Initial concentration, this is 0.2 molar water. It's a liquid. This is nothing before ionization. Our change is minus x and plus x and plus x. And at equilibrium, we have 0.200 minus x. Water doesn't matter. We have x and we have x for these two. The expression for Kb is going to be concentration of our Hb plus times concentration of our OH minus divided by concentration of B, the original base. So this will be equal to, actually in our chart, it's equal to x times x in the numerator divided by 0.200 minus x. So we can find Kb if we know what x is, which should not be impossible to find, because x is equal to the concentration of hydroxide ion at equilibrium. So the pH is 10.92, so that means the H plus concentration is 10 to the minus 10.92. So we can find the H plus concentration from that, and that is equal to 1.2 times 10 to the minus 11. That's H plus concentration. So that means OH minus concentration is Kw, so that's that 1 times 10 to the negative 14th, divided by 1.2 times 10 to the negative 11th. And that's OH minus concentration, which works out to 8.3 times 10 to the negative 4th. That's OH minus concentration, which is X. I'm going to show you another way that we could have done this. We learned, remember, that 14 is the sum of pH and pOH. So pH is 10.92 plus pOH would give us 14. So if I take 14 and I subtract 10.92, I get the pOH value is equal to 3.08. And so that means the concentration of OH minus is equal to 10 to the negative 3.08. And that ends up being 8.3 times 10 to the minus 4. So either way you do it, you come up with that same value. Just do whichever one you're most comfortable with. All right, so now that we know that, we can substitute this in here. Since X is concentration of OH minus, we can say 8.3 times 10 to the negative 4th squared in the numerator. And in the denominator, you can put 0.200 minus 8.3 times 10 to the negative 4th. Or you can just forget about it in the denominator, because that's very small compared with 0.2, and it won't make a difference. Then do your calculation. And you end up getting 3.5 times 10 to the negative 6. That's the value of Kb. This concept, we're going to relate the Ka of an acid and the Kb of its conjugate base to each other. And we're going to do this by adding a couple of equilibria. So let's take a generic weak acid, HA, It reaches dynamic equilibrium with H plus and A minus, and the K for that reaction is the Ka value for this acid, HA. Then let's think about its conjugate base, A minus. It will react with water and produce a dynamic equilibrium where it has the conjugate acid, HA, and OH minus. The K for this reaction is the Kb for the conjugate base, for A minus. Now imagine that we add these together. What do we get? Well, the A minus cancels out on both sides, and the HA cancels out on both sides as well. And what you're left with is water just auto-ionizing. Well, by the rule of multiple equilibria that we learned in the last unit, the K for this reaction, because we added two equations together, is the product of the two Ks for the two reactions that we added together. So that's the product of Ka for the acid times Kb for the base. But we also know that this is equal to Kw, because that is the value of K, that is the name for the K for this reaction, Kw. So if you put that together, we have a relationship that can allow us to relate Ka for an acid to the Kb for its base. So here's an example problem. What is Kb for NO2 minus ion if the Ka for HNO2 is 4 times 10 to the minus 4th? So if you think about what's going on when HNO2 functions as an acid, it's going to produce H plus ions, and it's going to produce NO2 minus. So NO2 is the conjugate base of HNO2. And we have this relationship here that says that Kw is equal to Ka for the acid, so in this case for HNO2, times Kb for the base, which in this case is NO2 minus. So if we want to know what Kb for NO2 is, we can just kind of solve this equation. So Kb for the NO2 minus ion is equal to Kw divided by the Ka for HNO2. So Kw is 1 times 10 to the negative 14th. That's that constant. It's at 25 degrees C, at least. It's always unchanging. And then HNO2, well, that's 4 times 10 to the minus 4 for its Ka. So this quotient will give us Kb. And the Kb here turns out to be 2.5 times 10 to the negative 11th based on that. Here's a problem. What is the pH of a 0.2 molar solution of NaC2H3O2? And it gives us the Ka for HC2H3O2. And the reason for that is because if you look at this acid, and if you look at the anion here, in NaC2H3O2, it's its conjugate base. So here's what would happen in this solution. The NaC2H3O2, because it's a group 1 salt, is going to completely dissociate, and you're going to get sodium ions in solution, but also C2H3O2 minus ions. That ion is the conjugate base of that acid. So what do we really have here? We have C2H3O2 minus ions. Because that's a weak base, it's going to react with water, and it's going to produce HC2H3O2 and hydroxide. And we want to know what the pH is. We can get that by figuring out what's the concentration of OH minus at equilibrium. All right, if we had a 0.200 molar sodium acetate, that's the name of this ion, solution, and it's 1 to 1 to 1, that means the concentration of sodium ions is going to be 0.200, which we don't care about, but the concentration of acetate ions is also going to be 0.200, and we do care about that. So that's their initial concentration before ionization of our weak base, 0.200. Water's a liquid, we don't care. Before ionization, there is neither hydroxide ion or acetic acid. That's the name of this acid. What's the change? We're going to lose X of each of the reactants. We're going to gain X moles per liter of each of the products. At equilibrium, then, this is 0.200 minus X. Still don't care about water. These are both X. All right, so Kb here would be equal to concentration of HC2H3O2 times concentration of OH minus divided by the concentration of the base, which was C2H3O2 1 minus. But we don't know Kb, so we can't solve this problem. So we'll have to figure out what Kb is. But remember that Kb times Ka for the conjugates are equal to Kw. So as long as you're talking about the A for the acid and the B for the same conjugate base, that this relationship holds. So that means my Kb, which is what I want to know here, is equal to Kw divided by Ka. So Kw, 1 times 10 to the minus 14th, Ka, 1.8 times 10 to the minus 5. So our Kb value is given by this ratio. And that ends up being 5.6 times 10 to the minus 10th. So that means then that 5.6 times 10 to the negative 10th is equal to X squared divided by 0.200 minus X, or because 10 to the minus 10th is small, you could drop that as well. And then you could use this to solve for X. And X is going to be concentration of OH minus, so that's why that would be useful to solve for X. So I multiply both sides by 0.2, or solve the quadratic if you want, and then take the square root. Either way, you're going to come up with a hydroxide ion concentration of 1.1 times 10 to the minus 5. So that means that the concentration of H plus is going to be equal to Kw, which is 1.00 times 10 to the minus 14th, over the concentration of OH minus, which is 1.1 times 10 to the minus 5, which comes out to 9.5 times 10 to the negative 10th. That's H plus concentration. So pH is what we're trying to find. That's the negative base 10 logarithm of 9.5 times 10 to the negative 10th. And that ends up being 9.02.